It's a real pleasure to share with you some of the things that our laboratory has been thinking about and doing in recent years to try to help people with a wide range of neurological diseases and disorders, in particular paralysis. And so this afternoon, I'll really represent the wonderful work that my students and postdocs, our medical residents and fellows, and all of us do here as part of the labs. So without further ado, let's take the coming 25 or so minutes to talk about implantable medical systems that we've all become very familiar with over the past couple of decades. And this cover of Science back in 2002 really sort of illustrates that we've all become comfortable with various types of different implants, cardiac pacemakers that help our hearts beat regularly, artificial knees and hips. And, you know, the bionic human might be a little bit overstated, but it gives us this real sense of what the future could look like, where we can actually go in and replace or bypass a whole variety of injuries that don't really fit into the model of surgery alone or pharmaceuticals alone. It's somehow new and different. It's electrical, it's mechanical, and so forth. And what's really happened in the last 20 years, as exemplified in this cover article in The Economist, is that the brain is really thought to be this next frontier. And what this really reflects is something rather remarkable. And that is that we are starting to really think credibly in science and in medicine about interfacing with the brain, treating the brain as a computational system, understanding that the brain communicates largely electrically. It also is very importantly dependent on chemical transmission, neurotransmission, and that's why drugs have an effect. And what we can do is we can think of this 3-pound sort of, chunk of meat, if we're speaking informally, as a remarkable place, but unfortunately we can do very little to repair it currently. Let's try to change that. Now, to start off, let me remind all of us of what we actually have also become a little bit familiar with. And that is that there are several medical systems that write information into the brain, okay? And this is meant to indicate that we can send signals into the brain to replace lost functions. For example, retinal implants, a company called Second Sight and several other startups are starting to do this, where you put a little camera, not unlike your cell phone camera, at the back of the eye on the so-called retina. And then what it does is it transduces light, and it then creates a pattern of electrical stimulation that activates the optic nerve that goes through your brain, and it provides some semblance of vision. Now, you can't read, it's not that accurate or precise, high resolution, but you can definitely tell where openings and doorways are, where objects are, and this is really remarkable. And this is coming a long way, and these types of technologies have been around for some time. Cochlear implants are sort of the origin story, the granddaddy of them all, if you will. And this is a small coil of stimulating electrodes that pass electric current into the inner ear called the cochlea. And it does so because it has a microphone and it picks up sound. And then again, it produces patterns of electrical stimulation, which have become so advanced that they actually allow people to acquire spoken language, even if they're born congenitally deaf. And so I think that if I were to ask for a show of hands, some large number of you actually will know, either by 1 or 2 steps removal, somebody that has a cochlear implant. Now, rather newer, but still FDA approved and going in all the time in the last 15 years or so. In fact, my partner in all the things I'll be sharing with you, Professor Jamie Henderson, who's the head of functional neurosurgery here at Stanford, puts these in several times a week, every week right here at Stanford. And what this is a so-called deep brain stimulator, which is an electrode a few inches long that's neurosurgically implanted to a deep region of your brain called the globus pallidus. And through a wire that's routed under the skin to a pacemaker-like unit, it trickles electrical current in, and that electrically stimulates cells and disrupts aberrant neural activity. And actually, nobody really knows exactly how that works, but that is sometimes often the case in medicine. Nevertheless, what it does is if you are suffering from Parkinsonian tremor, when you turn this electrical system on, the tremor stops. And so people are walking around, hundreds of thousands of people worldwide, who constantly have electrical stimulation routing into their brain to suppress tremor. And the final system is very new. NeuroPace is a company just down the road. Medtronic, of course, is a very large company based in Minneapolis. But NeuroPace attempts to sense the oncoming electrical storm associated with epilepsy, make a decision, yes, there is going to be an epileptic seizure, and then it sends electrical current out to a different set of electrodes to try to avert the electrical storm from ever happening in the first place. And this is the so-called closed loop. It senses and it disrupts, okay? And that leads naturally into the other type of system. So, very, very creatively, I flipped the arrow here, right? So now what we are doing is we're reading out information from the brain. So when we are preparing to move or a variety of other brain states, if we can measure from enough neurons at the same time, we can do some potentially interesting things. So again, this deep brain stimulator is now paired with a sensing system. So not only are you trickling electrical current in, but it has electrodes so it can measure neural activity. And then it can go into a feedback loop where it can say, oh, I stimulated, I see how the electrical activity is changing. I think we need a little bit more stimulation. It can do that on its own instead of needing to go into the clinic all the time to get tune-ups, okay? Another is this epilepsy implant, where now I'm just showing you the electrodes associated with sensing and stimulating, where this is really a decision-making unit. Okay. Now, those are existing systems or systems that are FDA approved on the way out. But let's, on this afternoon, go on a little bit of a mental journey, okay, and imagine a future. Let's imagine a future where it's possible to record or measure electrically from thousands or even millions of neurons. Now, there are about 10 to the 11 or 100 billion neurons in your brain. And so currently systems are measuring from a few hundred. I'm here saying maybe a few thousand or millions, but this is still a tiny fraction of the total number of neurons. So let's keep a question in mind. Is it really possible to do anything useful listening in on such a few number of neurons? The answer will be yes. We can imagine stimulating now thousands or millions of neurons also. And what if we could do that in fully implantable, ultra low power systems? By that, I simply mean no big bulky connectors or other things, but fully implanted in tiny little packages that can need recharging, of course, but maybe that's only every few days and through the skin, not unlike your electric toothbrush with inductive powering. And finally, what fuels all of this is our neuroscientific understanding of what to measure and to what to stimulate. And this is really the revolution that you've probably all heard of, which is neuroscience, you know, the frontiers of science of trying to understand how the brain works. So let's be even more concrete, and let me, in a couple of slides here, zoom in on the exact problem we are tackling. And then I'll show you a couple of the systems that we've built to help people. And then we'll move to question and answer here in a bit. So millions of people really suffer from paralysis of a wide variety, but some types of paralysis are so severe, as this picture of Christopher Reeve reminds us. Okay, for those of you too young to remember, Christopher Reeve, before he passed, was Superman in the movies. And in the mid-90s, he was thrown from his horse and severed his spinal cord. And from that day forward, was not able to walk or to move his arms. And less appreciated, he couldn't speak clearly either because of the need for ventilation. And despite being a person of considerable means and actually starting the Christopher Reeve Paralysis Foundation, which has actually funded some of our work, he passed, unfortunately, many years ago, really being in no better state than he is as shown here. But what this picture brings to mind is a fairly age-old idea, which is, I wonder if the intentions or the desires to move are really still fairly normal in the brain. And it's just that those signals can't get out the spinal cord on to stimulate the paralyzed muscles here, or stimulate the muscles and move your arm. So can we eavesdrop in on that electrical activity? Well, turns out, yes, you can. So let me zoom in one level more on the same problem. And this is a side picture, of course, of your brain. And if you see a coffee cup that you wish to reach out and pick up, you first of all detect where the cup is by seeing it on your eye. And then you know how your eye is angled in your head, and the brain does all these remarkable calculations. It sees where that cup is, and then it starts formulating initial plans to move your arm there. And then those plans are elaborated into detailed signals to control the arm that are sent down the spinal cord, activate all the different muscles in your arm at different forces in different ways, working through all your joints and ligaments, and cause the arm and hand to move over, pick up the coffee cup. Now, if there's an injury here, which is what we're considering, we could, for example, implant a tiny little electrode. Okay, and this is a little chip, literally a computer chip made of silicon, okay, in a very particular way that I'll expand on in a second. And from that, we could then measure the electrical activity of many neurons. I'm showing you about 3, but I want you to start thinking about maybe 100 or 200 neurons. And these tiny little blips show you voltage versus time, and they're about 1 millisecond long. And these are these little pulses of electricity that one neuron uses to communicate to the next. That is the language of the brain. That is believed by modern neuroscience to be how all cells communicate with each other that are at any distance. Okay, there are some other fine points of how they can communicate. And it's really the rate at which these action potentials, so-called, or spikes, sometimes they're called, are emitted that encode the information. More on that in a minute too. So we can measure these signals, and then we can come up with detailed mathematical algorithms, decoding algorithms, that are run on low power integrated circuits that could actually be implanted right there as well. Then those signals could come out and do one of 3 things in this particular case. It could stimulate the paralyzed muscles of the arm, and that is shown here. Our colleagues at Case Western Reserve have done this. A couple of electrodes come out through wires. You compute how you want to stimulate all these different electrodes surgically implanted in the muscle bodies all over the arm. and the arm is able to pick up a coffee cup and bring it up for this participant to drink. Another example is to control a prosthetic arm or a robotic arm. Now, this robotic arm isn't naturally, it doesn't look too natural, okay? But you can imagine much more sophisticated ones that DARPA and NIH have made in recent years. And again, by thinking about moving the arm, those signals are read out and move that robotic arm to bring a coffee cup up. And this is wonderful work done by our colleagues at Brown University and Pittsburgh University. Now, those are wonderful systems. They're very important, and I'm not going to talk about them. I'm going to instead talk with you about this third, which is to interface with the computer. And what's going on here is that we took a very deep bet about a decade ago. And at the time, it was seen as a little bit strange, perhaps, but welcome to research. And that was to say, you know, we'll bet that more and more of a person's life is spent interacting with electronic devices. So if we pause for a second and ask ourselves, honestly, be honest, how much time each day do you spend in front of your cell phone, your tablet, or your computer, right? And of course, if you're a parent like I am, you are pretty aware that at least with kids, that's a very large number, but it is also for us as well. We spend an awful lot of our time doing this. So if we had an injury that prevented us from working or communicating well, if we could communicate with computer devices of all flavors, that would really restore independence. And independence is the number one thing that people with quadriplegia, so-called tetraplegia these days, wish for. So let's build this system. I'll show you a couple of videos of how they work, and then we'll go to questions. So what is this sensor? Here's a sensor shown next to a fingertip. It's about 4 millimeters by 4 millimeters. It is made out of silicon. It's made on the same semiconductor manufacturing lines as many other computer chips. So particularly these days, where most of us are aware of the great chip shortage, fortunately, these aren't being too badly affected, but they could be. And what's protruding out here are 10 by 10, so 100, tiny electrodes, each about 1.5 millimeters long, very thin. And that is the distance that's going to be inserted into the outer surface of your brain, called the cerebral cortex. Now, this is done, of course, under full general anesthesia at the hands of extremely skilled neurosurgeons. Here's how it works. So imagine that in the operating room, you expose some of the brain. Of course, the rest of the brain is intact to a skull and so forth, but you expose a little bit. You put the the sensor, the so-called array here, and then hopefully you're seeing this play reasonably smoothly. You can see the electrode sitting there, and then it is inserted into the brain, okay, at about a 1.5 millimeter depth. And I want to then zoom in on what the tip of each one of these electrodes is doing. And what it's doing is that it's coming to rest very close to individual cell bodies in the brain. So what I'm showing you here is one neuron, one cell of the brain. And this is communicating with this cell over here by emitting those tiny little voltage deflections. Think maybe 70, 80 millivolts, okay? And I'm sorry, microvolts, and about 1 millisecond in duration, okay, is what we typically measure here. Now, the tips of these electrodes will pick up on nearby neurons firing these active potentials. And across the whole electrode array, you can imagine how each one of these tips is picking up for 1 or 2 or 3 of these neurons. So overall, we're able to measure from a few hundred individual cells. And they're each telling a different story about how you want to move your arm. So for example, if you want to move your right arm to the right, then some of these cells are going to fire a lot of these action potentials, whereas other ones are not going to fire very much at all, not emit those action potentials very much. But if you want to move your right arm to the left, you may find the opposite pattern, and the same for up and down. So there's a unique pattern across populations of neurons that allow us to not just say, oh, the person wants to move their arm sort of to the right. It's very precise and mathematical. This is how many millimeters per second at exactly what angle in three-dimensional space, okay? And this is where tens of PhD theses from my lab have come to really understand the signal processing and the machine learning of how to interpret that set of signals. Then what we need to do is bring the signals from those electrodes out through wire bundle to a connector, okay? And that connector protrudes slightly through the skin, and that's the current system, but I don't want you to think that that's the future. The future is getting rid of all this and just having a tiny little chip back here that sends out, for example, Bluetooth signals, just like so many of your other devices. And then just during the session where we're recording, we can plug in an amplifier, but again, I want you to think about this all being gone. And this is where the signals get amplified and sent to the computer. Now, I'm going to tell you two brief stories, very brief. The first is oriented on this words per minute scale, where you can see that people that need to use a so-called sip and puff interface, if they're not able to move or talk, or other natural types of systems like conversational speech is at 150 words per minute, professional typewriting is maybe 75, and so forth. And I'll show you how it looks very mediocre on this scale, but it's way above zero, and we are creeping to the right here, where a two-dimensional cursor can be controlled with one's mind, so point and click. And the second story will be this brand new brain-to-text system I'll describe. So I will not go through this in detail, but full credit to Vikash and to Chetan, who are now professors on their own, where we built a system that takes these neural signals out, does a variety of electrical engineering signal processing to get out low frequencies and high frequencies from these signals. And then this green box is the decoding element, the mathematical element. For those that you may know, Kalman filters, a lot of it's built on that. More recently, this is all replaced with the current neural network, machine learning AI algorithms. And then that is driving this white cursor. And here's how it works. So here is one of our participants, T6, who has, unfortunately, amyotrophic lateral sclerosis, ALS, or Lou Gehrig's disease, is unable to move her arms or her legs, and unable to speak clearly. And we have one of these electrodes implanted. You can see the amplifier here, which is only plugged in when we're doing the experiments. She's looking at a screen, and she's going to be controlling this little white computer cursor. It's going to slide however she wants in 2 dimensions over the letter she wants to type. And then what she's going to do, instead of thinking about moving her right hand up or down or left or right to move the cursor, but is to squeeze her left hand. And by squeezing her left hand, what she's able to do is click, okay, to select the letter. So let me play the video. And if I get lucky, it'll be smooth. If not, I will hand mimic it. So I see on my end, at least, unfortunately, it seems to be lurching, but it moves continuously, I assure you. to type out on the screen an answer to the question, how did you encourage your sons to practice music? And she's typing when they started their lessons. Okay, now I apologize for this, I think not moving smoothly. So what I'm going to do is I'm going to manually do this at about the right rate. Sorry about this. But imagine this cursor just moving slowly. And then when she wants to select a key, she squeezes her left hand, it turns blue, and that letter is copied up above to slowly type out, just like you or I would on our cell phone keyboard, software-defined keyboard, type, and it would get transferred up into a text box, for example. And we're able to achieve about 24 correct characters per minute, okay? And at about 5 words per minute, you get about 7 or 8 words per minute. Now, that's fine, but I just want to control a tablet, okay? So sort of the culmination of this line of experiments is we just bought a tablet literally from Amazon, didn't change a single thing, and actually didn't even use accessibility mode, which makes things larger on the screen, and asked her just to go ahead and control it. And this is where, for the first time, you get things like word completion and so forth. So she's looking at this tablet here, and I've copied it up here larger so you can see it. And again, I apologize, the video seems to not be moving smoothly, but this is the cursor that she's moving. And I'm just going to take over here and sort of hand animate it. So the cursor is on the screen, and she's typing out orchid because she's an avid gardener, okay? And clicks, and then what she sees pop up in a Google search are a few more selections. She goes ahead and makes a selection, an orchid care. And then she's confronted with what we're often confronted with, which is sort of a wall of text that's not too appealing. And note how small the letters are. So what she does is she says, well, I could select these, and I may, okay. But what I really want to do is I want to go just look at some pictures. So she goes back, as you can see here, and she goes to image search, as you or I might. And then she just goes ahead and selects images to see a nice picture of orchids and select the one that she wants, okay? And how do we know that she's getting the one that she wants? Well, we can ask her and she can let us know. Okay, that's moving a computer cursor in 2D and selecting it. That works very well. You need those types of systems, but what if what you really want to do is type as quickly and as accurately as you can, just like you or I might on our keyboard. And we don't really care how our finger moves to get there. We just want the text to appear quickly. So Frank Willett, wonderful postdoc and now research scientist in our group, had the really nice idea of saying, well, you know what people can do is attempt to handwrite, because we all know how to handwrite. And what that's really doing is it's a very insightful way to have very rapid motor commands generated, okay? And we're recording in the so-called motor regions of the brain, motor cortex. And so this thought bubble is imagining or attempting to write HELLO space W, hello world, okay? Little computer science joke, okay? And we record from these arrays, and what gets typed on the keyboard is HELLO space. Now note, the W isn't yet complete, so we haven't seen all the neural evidence of what character that is, so we should wait, and we do. And then once it's completed, we can say, oh, that was a W, and then type up a W. And the second very important thing is we are not attempting to reconstruct penmanship, not the exact way you write the H and the L. We just want to know, is this an H or is this a Q or is this an A? We just want to type it, okay? So that's a classification problem It's related, but maybe it's a little bit easier. So again, we put these electrode arrays in to this characteristic little so-called hand knob area, okay, where those electrodes are sitting in the area of the brain responsible for the hands and the arm. This is a so-called homunculus, motor homunculus, okay? And we start off by asking our participants to attempt to write the letter A, prepare to write the letter A, then please attempt to make it. Thank you. How about preparing to write the letter M? And we do this randomly through the alphabet many, many, many times to collect training data, meaning we know what our participant was trying to write and we have the neural signals. Now, can we reconstruct the imagined pin tip trajectory from this neural activity? So we need to have existence proof that we can actually get meaningful signal from the brain related to those hand movements. And the way we can do that is we can take in the neural activity, which you can imagine to be a vector of the length of the number of neurons you're recording from. And then there's some matrix that you multiply it by, okay? And out pops the horizontal and vertical pin tip velocity. So probably half of you like the little return trip to math, and the other half of you, it may have sent chills about past experiences. That's natural, that's fine. And what we're able to see is that when our participants attempting to write the letter A, we can see that from the brain activity, we can reconstruct the letter A and B and C and D. Now, wait a minute, Krishna, you were saying you were not trying to reconstruct the penmanship. That's correct. We actually don't care that this A is not excellent or this B or the C aren't. The key point is that these are different. The fact that they're different and they're different from each of the different letters is the key, because that means we can tell them apart. Now, how well can we do that? And how well can we do that on a so-called single trial? So if I try to write one letter, not an A on average, but that A, well, we can take the neural activity, which lives in the so-called high dimensional space. We can reduce that dimensionality down with so-called machine learning and dimensionality reduction. This is not unlike taking a three-dimensionally bent paper clip, shining light on it, and then looking at its shadow. The paperclip is 3D, but the shadow is 2D. That's a dimensionality reduction operator, okay? And what you see is that all the G's and all the S's are pretty easy to tell apart. You can draw a line through there, where each of these dots in red are all the different G's that the person attempts to write over an hour, for example. Same thing with F and T, and all of them, except here you get a little bit of a mess, but it turns out that if you rotate this, they split apart. And they do that well enough that 94% of the time, we can tell the correct character. So that gave us good encouragement to go build the system. I'll just show you how this works and we're done. So he can attempt to write a letter and then many letters after the other to get a word. And we have our neural activity, the function of time. We take a little bit of data at a time that scrolls along as time progresses. We can run it through our decode algorithm that I will not go into more, but this is a so-called recurrent neural network, one of these modern machine learning algorithms. And out pops the probability of each letter as a function of time. So here's a T and an N and an E. And if you drew a line and you just picked which letter was above it, you would get what we call the raw output, TNE paper. Well, I don't know what TNE paper is, but I know what the paper is. So this is a mistake, okay? And fair enough. We make a mistake about 5% of the time. And it makes sense that would confuse an H and an N because those are pretty similar in physical space. So you could just live with it, because we often text each other with mistakes and we don't really notice it unless, you know, your phone word corrects and mangles it so badly. But we can do much better. We can do much better because of modern machine learning language models, which capture all the probabilities of transition. If you have a T, it's 90% likely that you'll go to an H in comparison to going to an N, and so forth. So you can intersect what is known about the statistics of the language with the evidence coming from the brain in real time to effectively correct these errors and reduce that error rate of 5% down to 0.5%. So now you're typing at 99.5% accuracy. And you're doing so at 90 characters per minute. Okay, and this is a video showing that. Now here's a participant of ours where now we have 2 electrodes implanted. You see 2 cables. And again, these are only attached when we are there with him running these experiments. And we have a sentence typed out here, felt like a soldier on a battlefield. And the right character here is what we ask him to attempt to write instead of a space. It's far easier to detect a symbol than the lack of a symbol, which is what a space is. And now here, you'll see letters pop up. And if I showed you video of his hands are absolutely still because he's paralyzed due to a spinal cord injury, okay? So he's just thinking about handwriting, and this is what pops out. Okay. So again, it's a little jerky. It's doing a little better this time. It's absolutely smooth in reality. Okay, and you can see that letters just get typed out here. And this is building on top of the previous system, the 2D cursor, which doubled world record performance. This system doubles it again. Okay, and this is a field where every 5 or 10% improvement is a huge deal. So these are pretty substantial leaps. Okay, final thing is I'll put those 2 side by side. You've seen this bottom movie. I've just showed you the upper movie, but it turns out that we ran both the 2-dimensional system that I first showed you in the same participant that we also had the opportunity of working with the handwriting. So instead of 8 words per minute, we're now doing about 17 words per minute. And the video simply shows the 2 systems running at the same time. Okay, so at least on my screen, for some reason, this looks like it's playing correctly. Hopefully it is on your monitors as well. So the cursor is moving continuously and smoothly, and he's selecting, you must be the, but you see here, you must be the change you wish to see. This is going twice as fast, okay? So, in conclusion, these so-called intercortical, because we're putting electrode arrays into the outer surface of the brain, the cerebral cortex, brain-computer interfaces that decode brain activity are really advancing rapidly, okay? And this is enabled by new neural interfaces, meaning these sensors, low power electronics, and very importantly, neuroscience discoveries. These new BCIs, IBCIs that guide 2-dimensional cursors more than double previous communication rate methods, and that's enabled by new neuroscience knowledge that we brought to bear and new machine learning decode algorithms. And I know that in the text box, Tanya is going to be putting links in case you just want to look at the original paper. Okay. And the same again here for this new handwriting IBCI, which again doubles performance. And this is also enabled by new neuroscience and machine learning. And there's also a link to a recent paper where you can recognize these letters that you've now seen on the cover of Nature from back in May. So finally, the most important slide I ever show, and unfortunately I don't have time to go through it in more detail, that's why I put some pictures in. I want to thank, obviously, the just absolutely brilliant students and postdocs and spectacular staff, collaborators, former students in the recent past, and lab alumni. All of our funding agencies, my endowed chair from Hong Se and Vivian, WM Lim, and also for full disclosure, I'm on a number of scientific advisory boards. The two most relevant is that I'm a consultant with Control Labs, which is part of Facebook Reality Labs, or now Meta. And also I co-founded and I'm a consultant with Neuralink, which is Elon Musk's company in this space. Thank you very much.
Thank you, Krishna, for such an amazing presentation. We have a lot of questions from alumni, so I'm going to jump right in. The first question is, does the deep brain stimulation also work for depression?
That is a great question that has been investigated specifically for that indication, depression. The results have been a little bit mixed, but the belief, informal belief in the field is that yes, it can. And there are new clinical trials starting up to go after that. There's really exciting work with transcranial magnetic stimulation right here at Stanford, where you send a pulse of electricity, it sends a pulse of magnetic energy in that causes activity in the brain. And that can also be used very helpfully for refractory depression. It's not electroshock therapy, it's sort of in between.
Thank you. We have a great question from Jeff Butler. As an MBA1 living with a spinal cord injury, this technology is really exciting. What is the current technological blocker to getting BMIs into people? Is the Utah array sufficient to get this done, or are companies like Neuralink going to hold the key to commercialization?
Yeah, that's a great question. And I definitely feel for you. We need to get this technology out quickly. I don't say that because that's our work. I say that because that's really the ethos at Stanford, which is basic science, engineering, proof of concept, terrific. Well, let's also get it to people. It absolutely, as you suggest, has to involve companies. And the challenge here is that these are medical device companies with enormous capital expenses associated with them. So think computer chips, not software, right? Large investments. And the technology is sufficient, I believe, personally, not maybe the Utah array in its exact current form, but a scaled up version of that, which is what Neuralink is working on. There's a few companies working on this. I think that technology with what we know can absolutely help people today if all that were built, if all that were shown to be functionally useful and safe. Of course, our job is to show that it can be done. Our job is to show the proof of concept. And then finally, FDA approval and the whole enterprise of taking it out there. This is my personal motivation for being involved on a weekly basis as a consultant and as an advisor and co-founder. And I think that Neuralink's founding, Elon Musk's entry, controversial individual to be sure, but that jarred probably around $1 billion of VC funding into the field. So stay tuned. I hope that it's much faster than I would have even guessed 5 years ago.
Here's a great question from Kieran Mundy. Does it matter where precisely you embed the electrodes in the cerebral cortex?
Yeah, that's a great question. So there's a fundamental principle of so-called functional organization. Different parts of the brain are largely responsible for different functions. So at the rear of your brain in the occipital lobe is primarily vision. And in the frontal, just anterior or forward from sort of your ears is where motor commands are shown. That's where we implant. And even further ahead, the so-called frontal lobe, as you know, that is executive function, decision-making. So yes, it does matter where you put it because you'll get stronger signals related to what you care about. But it's also an excellent question because the brain is so-called plastic, meaning it can change its functionality and it can adapt to what it's controlling. This is a huge thing in cochlear implants too, that your brain learns how to interpret those signals. The reverse happens on the other side. So you have, it's sort of like you have to be in the right state in the country, but then maybe you don't have to be in exactly the right city.
I have another question. Can you give references discussing how you interpret the sense electric fields from hundreds and thousands of neurons, especially how to separate overlapping signals from nearby neurons?
Yeah, that's a great question. Yeah, I'd love to have you in the lab. So this is the so-called blind source separation problem. So one electrode could hear, for example, two neurons, one closer, one farther away. The one that's closer, because it emits the same size action potential roughly as the one that's farther away, will be measured as larger by this electrode. And so that gives you one way to tell the two neurons apart. Okay. The other way, if they both are firing at the same time and therefore actually add together, it's an extremely so-called linear material. Okay. They just add. Then you can invert it because you've learned the shapes of the two constituents, and you can probabilistically say, oh, what I'm seeing is a mixture of these two. So there is a way to do this. It's called spike sorting. It's an entire sort of cottage industry. And it works okay with one electrode, but the real answer to your question is by putting higher density electrodes, you can have multiple electrodes picking up on the same neuron. That's like having a quadraphonic recording of a speaker and then another speaker in a room, like in a cocktail party, and then you can do a really good job.
What is the prognosis for non-invasive implanted EEG/BCI to help people with ALS to communicate?
Yeah, that's a great question. So first of all, there's a range of technologies. And in this short talk, I didn't have time to go into it. But if you put electrodes on your scalp, that is called EEG. This is done all the time in neurology. If you may be having seizures or other things, that is what will be done. And broad waves can be interpreted and it can be diagnosed, okay? Now, if you put those same electrodes below the skull, but on top of the outer skin covering your brain called the dura, that's called an ECOG, electrocorticography. And you can put it above or below that dura. Below is called subdural. And then finally, what I was showing you, which are little electrodes that go right next to the source. Now, I'm personally a huge believer in all of them, okay? Many in the field are not. They sort of love their own technology. That is not my view. This is just the technology I work with because I actually want to know how individual neurons work. I'm also a neuroscientist, okay? The trade-off is that if you measure from farther away, like outside your skull, you cannot currently, and people have really tried quite hard with truly sophisticated signal processing. So it's not like, oh, the right field hasn't looked at this. You can't tell individual neurons from each other. So what you get is an average across many, many, many neurons. And in fact, thousands of neurons. So you can tell, you can measure some information. You can use that to control a computer cursor, but to give you some rough numbers, you're able to do only about 1/5 as well as if you are inside, okay? So different people will want different treatments. Some people never want surgery at all for anything. That that's very, we respect that. You need to have treatment options for people that is their preference. Patients' wishes are always correct, right? Whatever a patient wishes, that is correct, okay? But some people will want the implant. Same thing, by the way, with Parkinson's disease. You'll typically go on so-called L-DOPA, a dopamine precursor that will abate the tremor. Often, however, that will not persist to be effective after a certain number of years. Some people may wish to have a deep brain stimulator. Some people may not wish to. That's absolutely fine, but we want to have an array of options.
A lot of great questions. Next question is from Eric Sabelman. The pins of the Utah array are rigid and the brain is flexible and moves with every arterial pulse. Published studies show damage to neurons and to pin insulation over time. How do you anticipate achieving longer lasting electrodes?
Flexible electrodes. That's a great question. Very sophisticated question, of course. Not surprising with this audience. So you're right. Young's modulus, the stiffness of silicon is enormous. And it's like taking a pin and pushing it into a bowl of Jello, right? Where your brain is Jello. If you take your bowl of Jello and you shake it, you'll get little tremors, okay? Same thing with the brain. This is why concussions exist, right? If you, boom, hit your head, your brain sloshes around, you get concussions. So there is a so-called mechanical impedance mismatch between that stiff electrode, as I was showing you, the Utah electrodes, and the compliant elastic, as it's called, brain. Now, newer technologies, but the reason we use the Utah arrays is that they are the only ones that are currently FDA approved, right? That's critical. We would love to simply buy other electrodes, okay? We don't make electrodes ourselves, okay? So other technologies, for example, Neuralink technology or Paradromics technology are coming in with different types of electrodes. For example, you could take a needle and push into the brain. These are very, very, very fine needles, okay? Don't worry. Push into the brain and then pull that needle back. And boy, you know, if you had a piece of thread through that needle, that's called a sewing machine. And when you pull the needle back, it leaves the thread there. Well, what if that thread is now made of polymers, okay, with tiny electrodes? And then what's left behind is totally flexible and moves absolutely stably with the brain. Does not have so-called micromotion that triggers the immunological responses because it's just sitting there signaling to the brain all the time that there's a foreign body. And you know what the body does to foreign bodies is wall them off with so-called glial cells. So flexible electrodes that have different types of immunosuppressants put on them. This is not unlike dexamethasone-coated cardiac stents and so forth. So you can manage that chemically as well.
Can this system work with debilitating migraines?
First of all, debilitating migraines are well, they're debilitating, yes. So this is a very, very serious condition. And unfortunately, I'm not aware of any work on these types of systems for that indication. So I apologize, I don't know. I'm not aware of anything, but that does not mean that it doesn't exist.
We have two related questions from, one is from Janet. When patients are using these brain to text systems, do they report fatigue more than we would if we were without injury? And then another one from Esther, when the patient writes letters with these methods, do their eyes follow the motion of the words they are trying to trace? And can they be tracked in neural activity?
Yeah, so these are great questions. So fatigue is a very important thing. The short answer is not much at all. Why is that? Because we're putting these electrodes in the areas of the brain that people use anyway to control that function. If you want to move a computer cursor on your screen, what do? You grab your mouse and you move your hand left, right, up, down. Okay, that's what we're asking them to attempt to do. So the fatigue is not high. It doesn't take a lot of cognitive effort. In fact, you ask people on the first day, hey, when you're using this, what were you thinking of? They're like, well, I was thinking about trying to move my arm and then seeing the cursor. And okay, you ask them after a week or two, and they're like, I don't know. I mean, I'm just moving the cursor. Just like if I ask you, what are you thinking about when you use your mouse pad? You probably say, well, not Not too much. I don't know. I'm paying more attention to the cursor and getting on with my work. Okay. I'm sorry, I forgot the second question, Tanya.
The second question, when the patient writes letters with these methods, do their eyes follow the motions words they're trying to trace?
Right. Yeah. So natural eye-hand coordination is that if I want to reach out and pick up this cup, well, it's going to be hard with my Zoom background, but if I want to reach out and pick up something over here on the left, my eyes will dart out to the target first and then my hand will follow. That's natural behavior. You're doing that all the time. You, of course, don't think about that, but that's what you're doing. So that is what people are doing here. Okay. Now, very importantly, in control experiments that I didn't share with you, we can have people hold their eyes fixed. We put up a little cross and say, please fixate that. We infrared track their eyes, and they can still use these systems just as well without their eyes. So it's not as though we're picking up on eye movements as a contaminant, okay? And also that absolutely just would not work for the handwriting, for example, okay? The other thing is that this is very closely related to a very natural question, which is eye tracking systems. Okay, now I could put up an image of the alphabet on the screen, like a keyboard. And if you said, Krishna, please write your name. It's a cod, meaning move my eye to K and then R and then I. And I could track that with glasses, and I could do really well, because our eyes are extremely precise, okay? So why not just use an eye tracker? Well, there's a couple reasons. One is that people are often given eye trackers, but it requires somebody to put the eye tracker on them. And then it ties up the eyes, which are extremely expressive element of human nature. So if you ask neurologists, what they'll say is, yeah, actually Medicare reimburses eye trackers. They're like 20 grand. We often give them to people, and in 2 weeks, they're in the closet. People don't use them, okay? And for higher dimensional control, like a robotic arm or other things like that, then the two-dimensional eye movements don't map to that problem very well.
A lot of amazing questions. I just have one last question. Where do you see this emerging technology to help people in the future?
Yeah, so I think so I'm a very conservative individual, but I do have to recognize that what we're talking about here is a very general proposition of interacting, interfacing with the brain, any part of the brain. There's not viewed to be any scientific or technological fundamental barrier, right? No physics has to be violated to do this. It will take time to engineer the materials. We could have a whole conversation on nanomaterials because we're still looking at bulk things, but why don't we think of things on the atomic scale and so forth, okay? So any part of our mental lives, any part of psychiatric, neurological, memory, Alzheimer's, there is a growing consensus that these types of interface systems, electrical currently, they could be optical, chemical, really have a very, very long, bright future ahead of them. Neuroethics is crucial. So I spend a lot of my day, a lot of my time at a variety of national committees and so forth on this topic. It is critical. And recent months and years with a variety of industries, even in social media, have taught us to be very cautious of just going out and build stuff. And this just couples back into the way any sufficiently innovative technology always is. How it is, by that I mean, there's always a benefit and there's always some not great use. CRISPR, Cas9, revolutionary, gene editing. could be potentially used to solve all sorts of human diseases. Companies all over the place. Jennifer Doudna up at Berkeley, Nobel Prize last year. But you could also have designer babies. And this has happened 2 years ago. Okay. Nominally to avert, a bad disease upon birth in twins. But, and of course, nuclear power is the granddaddy example of them all. So we have to proceed. You can never put the genie back in the bottle, but we have to do it cautiously. And it's critical, and academics, policymakers, everybody work in an efficient way to make sure that we stay on top of the ethics of this.
Thank you, Krishna, for presenting this groundbreaking research and giving hope to those people who are afflicted with paralysis or severe movement disabilities.
Thank you.